zoom in the camera. The main thing we're going to do today is some more center of mass stuff and work, some work integrals. I think I told you to read section 8.6, but only the first half of it, because the second half is about force and pressure and stuff and just gets super physicsy to the point where I was like, I don't want to think that hard about this. But the work, the center of mass stuff and the work integral stuff is like very mathy. So I just go ahead and do that, but I'll do some examples. Let me pull up the handout. I guess I can show you. There's the, yeah. Hopefully I'm being heard. Okay. What am I doing? Oh, all right. Sorry. Let me just get the. I uploaded a slightly new version of the handout, the physical integrals handout. I just added something to it. So I need to go to Notion and actually get to it. Let me do this. So I should share screen, shouldn't I? Okay, so handouts. Yeah. So still that same handout we've been using. That's fine. Okay, open, please. Thank you. All right. So first, what I wanted to talk about at first was the center of mass formula a little more because I kind of had to rush it at the end of class. And then the homework that you had to do just had a one-dimensional center of mass, so hopefully it wasn't too bad. And then point masses and stuff. But I want to do this two-dimensional example. And I assigned you some problems doing more dimensional examples. And then we can talk about what it means to calculate work, which is a measure of energy. And there's two different types of problems. One that, well, I'll get into this, but yeah, we'll get into two different types of work problems. But I do want to go, this formula I know is kind of throws people off. And then there's a formula the book gives and that I give that you can just sort of use to calculate. But I do want it to come from somewhere. So let me talk a little bit about the center of mass formula again, to try to give you a sense of where this comes from. So center of mass. All right, so just if you remember the point mass version of this, it was like, if I have some masses, like if I have mass M1 here and M2 here and M3, say here, and then there's some point I could balance this rod with my fingertip where it wouldn't tilt to either side, right? And the idea is the center of mass is that balance point. So balance point, and we call that X bar. So there is some X axis here in the picture that we're using. You know, we always coordinatize everything. And then the idea is, let's see, this distance right here. Well, this is going to be negative, but that's okay. That distance is, sorry, x1. So if this is at location x1, this is at location x2, and this is at location x3. Then I write down x1 minus x bar is the distance between these two. X1's less than x bar, so this will actually be negative. But that's okay because we want the sort of like, remember, it's the idea of the moment, right? Like the mass times the distance from the center. This is the center of mass right here. I wrote balance point, but I want to make sure it's center of mass. That's x1 minus x bar. This is x2 minus x bar. And I guess this distance right here is x3 minus x bar, right? Does that make sense? I'm just literally taking these distances. And the idea is that the sum of the moments, this is a weird word, moment, but it's somehow just mass times distance. We sort of seen that, you sort of feel it. Like we talked about, if there was twice as much weight on one end as the other, you'd have to balance it like 2/3 of the way towards the heavier mass. So it's not just the weight, but it's the weight times the distance from the center. So that's what this is. Some of the moments, so you'd have m1 times x1 minus x bar plus m2 times x2 minus x bar plus m3 x3 minus x bar equals 0. And the reason this works out is because this one's negative, right? It's that thing where you could put this on the other side and make it positive and sort of be like balancing left and right. But I think because we don't even know where especially if we have a lot of weights, it's hard to tell which two masses the center is between. That this is this nicer way to just organize all the information, put it all on one side of the equation, set it equal to 0, right? So did this part at least make sense of like how, like we would know, like there were problems on the homework, right? Where you knew like the masses and you knew the x1, x2, x3, and then you were solved for x bar, right? I just want to sort of see how we would solve this in general, right? So one thing you could do here is you could write this as m1 x1 minus m1 x bar plus m2 x2. I'm just distributing the masses through the parentheses. Check my algebra here, make sure I'm not doing something wrong. Right. And then I could move all the ones with minus signs over to the other side. And you get something like this. Love algebra. Doesn't it just make you happy moving symbols around on a page? No? Okay. So, right, we're given, I should say, like, maybe I should say that here, we're given M1, M2, M3, X1, X2, X3. And then we're solving for that. So the thing you could do that's nice here is you could then factor the X bar out of here, right? Right, just the right-hand side. You can factor out the X bar and then solve for X bar. X bar is, so there is this formula, but the physical principle it comes from is that the balancing out of the moments, the balancing out of the mass times distance. So if we solve for it, that's what we would get. Right. And one way to think about this is actually the total mass of the system, the bottom here. So we can also think of this as the total mass. One thing that might be worth doing is comparing this to, if you're looking at the handout, I have some similar formulas, but I'll write those out in a second, but I just want to put those on screen so you can see them at the top of page 2. So this is a formula for the center of mass of just a system of just 3 things. If you wanted to do this more generally for like endpoint masses, you can imagine for endpoint masses, instead of 3, on the next board. There's a lot of what we do in this class, right, is we write something as a sum. We do it for a few examples. Then we do it in general. Then we turn the sum into an integral, right? We've been doing that a lot kind of in this class. So, so for n point masses, instead of 3 here, what we would have is we would have the sum I equals 1 to n mi times xi minus x bar equals 0. Right, that's just the analog of that formula I wrote up there. Just I equals 1 to n. And then you can do a lot of the same algebra steps that we did up there, right? We could actually multiply the mi through and distribute the sum. So we could actually write the sum I equals 1 to n of mi xi minus the sum I equals 1 to n mi x bar equals 0. We just rearranged everything. I did 2 steps there. I multiplied through by the mi, and then I separated it into 2 sums. And then we could put this sum on the right-hand side. I just like to see how things generalize if we change like the 3 to n, you know? So that's the sum of mi x bar. And then now we could do the same thing we did up here, which is factor out the x bar. This is constant. So I can actually move it outside the sum, just like multiplying by a constant number. It's unknown at this time, but it's still a constant. So x bar times the sum I equals 1 to n of mi. And so that's where we had gotten to up at that point on the second line, second and a half line on the board. And then I can divide this sum, which again is the total mass. I'm just adding up all the point masses over to the other side. And so we get x bar is, there's 2 different formulas you can write down. You can write down this thing. Be lazy and not write the I equals 1 to n. You can write it like that. Or you can think of this as 1 over the total mass. Times the sum I equals 1 to n mix. So that would be the slightly somewhat generalized version of the point mass thing. Right? So this is just kind of things that you get formulas. But if you look at this and compare it to this integral formula, I mean, you can start to see some of the parallels, right? And in general, it's like if you have if you have continuous, so that's for endpoint masses, but for a continuous mass, like we did that example of the rod, and we're going to do a 2-dimensional example. We're going to do this number 5 with this metal plate in a second. So for a continuous mass, with density function, something like f of x, or, well, actually, I shouldn't say that. Be a little careful. Actually, let me just do this. For continuous mass, we have some, I'm just going to make like a blob. Okay. And if we slice it, a really thin slice, the width is dx, right? And then let's say the mass is, somehow we find some function so that the mass of the slice is just this thing, I guess. So the mass of the slice, it's going to be different in different scenarios, but the mass of the slice is given by some function times dx, because it's sort of like the area of the slice times some density or something like that, or maybe just the width, but something like that. That's like, it's actually a function. I almost want to use m, the function, I almost want to call the function m of x or something. And then, again, if we put it kind of like up there, if we put the x bar in the middle, if we put the x bar in the middle somewhere as the center of mass, we have our axis x, and this is at point x. And this distance is x minus x bar again. Right? So it's really analogous. Everything we're doing is really analogous. We're just doing it for a continuous variable x instead of like a discrete, like finite number of variables, x1 through xn. Then we want mass times distance. So mass times distance in this language now is, well, it's f of x dx times x minus x bar, which I'd probably write as f of x times x minus x bar times dx or something like that. And then that's what we're integrating and setting equal to 0. Because it's continuous now, we're going to integrate instead of sum. And I think if you look at the bottom of page 1 of the handout, you'll see, I guess maybe I should draw in here also like the boundaries. Like the leftmost piece is x equals a, and the rightmost piece, sorry, is x equals b. So that's like the boundaries. And then what we're doing is we're doing the integral. So the same thing, analogous to this equation and that equation, is that sum of moments equals 0 is that the integral from a to b f of x times x minus x bar dx. Actually, they're starting to look like plus signs. Sure. Are any of you the type, do you guys write your x like this thing? You can't do that. They're the people who do with the two little like. I wish I was that cool that I could write my x's are just like that. I wish I was cool enough to write x's like that. So I'm starting off by plus signs because I'm kind of leaning in there tilted. Okay. So this is the analog of that, just that this integral equals 0. And the exact same algebra steps lead to the exact same formula. Like here I multiplied through by the mass, and then I split up the sum into two sums, and then I move one over. Right here I multiplied through by the mass. And the two different sums, one involving x bar, one involving x1, x2, x3, move the ones with the x bar over. So you're trying to isolate x bar, right? So the same algebra steps give us the exact same thing. I know you've already done some problems on this. I just wanted to go over this, the concept a little bit more, see where the formulas come from. So same algebra steps as before. So like now we could do something like the integral f of x times x minus f of x times x bar, all dx equals 0. I just multiplied through the f of x through the parentheses, right? Then break it up into two integrals. Maybe I'll put the x in front. Minus the integral. Give these derivations enough time, it starts to be second nature, hopefully. I'm doing the exact same steps. I distributed the sort of mass function, and then I separated into two pieces. Then I move this one over to the other side. Then I factor out the x bar. Just trying to show you that this works the same. And now I can, x bar again is an unknown constant, I can factor it out. So again, all the same steps. I have them on the screen also. I mean, the handout, top of page 2 of the handout. And then it's worth noting that this thing right here, if that was the mass of the slice, this was the mass of the slice, and then we add up all those slices, then again, this is the total mass of the object. And that means x bar equals 1 over the, if I divide this to the other side, x bar is 1 over the mass times this integral. That's the same formula as before, just written in terms of integrals. And that's the formula I have on the handout also. Does that make sense? Just repeating the same algebra steps over and over again, just in different contexts, hopefully. Okay, that was very abstract. Should we do a problem? That'd be a good idea, right? Okay, so number 5 on this handout. You can pull it up on your own device, or you can so number 5. So a metal plate. Here, I'll draw this on the. I'm not going to share screen. I'm just going to draw the picture. We got a shape bounded by the curve y equals root x. The lines y equals 0, which is the x-axis, and x equals 1, which is a vertical line. So, okay, let me draw this. Number 5 from the handout. Here's a picture. There's x, there's y. Here's the root x graph. It looks something like that. And it says this is y equals root x. And it says this is x equals 1. This is y equals 0. Am I identifying these correctly? And so this is the object we're looking at. Thin metal plate, so we're really thinking about two-dimensional object. Constant density delta. Wait, no, sorry, I was reading number 6. Constant density 5 grams per centimeter squared. So this is length in these are in centimeters. This is in centimeters. So the density is constant. It's really helpful here to have constant density. 5 grams per centimeter squared. Right, it's an area density because it's a two-dimensional object. And so it says find the center of mass. So like now it's almost like we have this thin metal plate. 1 centimeter is very small, actually. It's a very small plate. I mean, I should have made it 1 meter. But, and you want to balance it on your fingertip. It's like you have this thin metal plate and you want to balance it. So you need to know both the x coordinate and the y coordinate of balance, right? So let's find the center of mass, x bar, comma, y bar. Can you guess anything about, this is height y equals 1. Can you guess anything about x bar and y bar? Just from physical intuition. Like if I told you x bar is 0.1, would you believe me? If I hold this plate horizontally, I can balance it somewhere over here. Yeah, so what could you maybe guess about x bar? Very, very broad. I'm not asking you to tell me the exact number. I'm saying, I guess I'm just asking, yeah. Yeah, so probably greater than a half. So probably, I just want to see if we get answers that make sense, right? So probably x bar is bigger than a half. What about y bar? Bigger or less than a half? Balance point of this thing. Basically, is it up here or down here? Like, I try to balance up here. Probably going to be less than a half, right? There's more mass down in the lower half. So probably these are true. Just like to give us a sense. If we get a number like 1.3, then we've definitely done something wrong. That's outside of the shape completely. So I just like to just sometimes use some intuition and see what the plausible answers would be. Okay, so now let's see if we wanted to find x bar. One thing that's kind of cool is that they are completely separate from each other. You can actually find x bar and y bar totally separate from each other. So like, if I want to find x bar, that is some x value. And now I want to look at distances like this, x minus x bar. So in fact, it's going to be that thing of slicing perpendicularly to the distances you're looking at. We're going to be integrating in terms of x. So let's do perpendicular slices. So for x bar, use use vertical slices. Sort of they're perpendicular to the distances that we're thinking about, right? We're thinking about x perpendicular to x distances. So if I just make a vertical slice here at x, and this is at x, and its width is dx. We need to do the area of the slice times the density, right? The density is constant, but we're going to have this x minus x bar if we started sort of up there with that formula, or x if we start with this, if we do this formula. So what is the height of a slice? What's the height of this rectangle? I'm at point x right here. What's that? I heard something. It's going to be in terms of x. I thought I heard someone say it, but yeah, it's just root x, right? Root x minus 0. I heard someone else say it too. Sorry. So it's just root x. So this rectangle has width dx, height root x. And so the area is root x dx. And so what's the mass? Notice this is centimeters times centimeters. So this is centimeters squared, right? Both dimensions are centimeters. And so the mass is the density times the area, right? So what's that? Just throwing a 5, right? Because it's constant. So 5 grams per centimeter squared times centimeter squared will give us grams. So 5 root x dx grams. So that's the mass of the slice. Okay. I mean, really, we're just kind of doing an integral, like, but we're throwing this 5 in. It's like if you're going to find the area, you would just do root x dx, right? But we're throwing this 5 in. But the other thing, so this is kind of our f of x in that. This is our f of x in that formula over there. Right, that's what I was saying, like f of x dx is the mass of the slice. So this is the f of x. And so if we want to find x bar, I could go back to the original formula and solve everything, but maybe I'll just use this formula that we have now that we've derived it like 7 times. Is that fair? So, I mean, you guys should be trying to get ahead of me and compute this. I mean, one thing is to find the total mass, right? What's the total mass of the object? And then to also find this integral where you stick the extra x in. Basically, you can see the total mass is that, right? So x bar is 1 over the total mass times the integral. Where do the slices start and end? What's the leftmost slice? X equals, a slice I think vertically, where's the leftmost slice? X equals 7? Okay, 7. You want to tell me the actual answer? 0? Thank you. The rightmost slice. 7, 1. Okay. And then we do x times 5 root x dx. But the mass is also just, if you think about the mass is like the area times the density, and we can find the area of that thing just by integrating the function root x, right? So it's just 5 times integral root x, but you could say it, you could rewrite it this way. Right? The 5 is just there to turn area into mass. So it's just this. These are 5s. Okay. So we can solve this, right? We can solve this. Actually, one thing's kind of nice, the 5s pull out and cancel. No, they don't matter. Actually, it makes sense that the density shouldn't matter for the balance point as long as it's constant density, right? You can see that in the math here, the 5s pull out and cancel. So this is the numerator, x times root x is x to the 3/2. I hope we get a number bigger than 1/2. You should get ahead of me and do it. Do it. right? Is that right? Is that what you guys are doing? What's 2/5 over 2/3? 3/5. That's 2/5 times 3/2. 3/5, which is bigger than a half. So that's good. That actually is a plausible answer. So X bar seems to be 3/5. Does that make sense? Yeah, question, please.
Wait, so how did you go from the numerator being x times 5 root x to x 3/2?
Well, I actually pulled both these 5s out and canceled them. So then it's just x times x to the 1/2, where you just add the powers, right? X to the first times x to the 1/2. And you add the exponents to get x to the 3/2. Good. Yeah, so I did a couple steps combined there. Other questions? Okay, what I want you guys to do, maybe we'll do groups where you're sitting, is try to find y bar using the exact same logic, but you're going to use horizontal slices instead of vertical slices. You already know the denominator. You actually already know it's 2/3 here. You don't have to do that again if you don't want to. You could do it again. But you're going to have to draw horizontal slices. Try to find the width of the slice at height y. All the x's are going to change to y's now. You're going to be doing dy, a function, the width times. So try to follow this. Maybe just like talk to the people around you, like try to start setting up, see if you can follow the same steps. So for y bar, you use vertical slice, you use horizontal slices. Draw a rectangle on that picture, like a horizontal rectangle. Try to figure out the width of the rectangle at height y. It's a little bit, that's the part that might be slightly tricky. The rest is just computation. So look to someone near you and say hi. Hi. Okay. So let's try to draw the picture, and try to figure out with the people you said hi to, the width of a horizontal slice. Slightly trickier than what we just did, but still not that hard. Yeah, the y center of mass now. Huh? You're underthinking it? Most Boda students overthink things. No, I should. It's not y squared. You have to draw that rectangle carefully and think about the right-hand endpoint and the left-hand endpoint and subtract them.
The width is or something minus 1 minus y squared.
Yeah, the right-hand endpoint of each little horizontal rectangle is the same. Think about that.
Yeah. So it's 1 right. The right hand will always be 1.
Yeah.
So do we still use the 5 when we're looking for y as well?
Yeah.
Yeah, the 5's there. I mean, it'll turn out to factor out and cancel again, just like the same, but if you wanted the mass of a slice, you would have to multiply it by the density. Yeah, the area of the slice times the density. Oh, exactly what I was writing there, and I was going to draw the picture again. Yeah. Sorry. Well, you'll have different, I mean, you'll have y and f of y and dy, and it'll be a different f of y and everything, but you can, yeah.
Okay, thank you.
I'm just going to draw this again and draw a slice.
Yeah, it should be, yeah.
You guys getting there with this? If you look back at the vertical slices, the top of the slice was y equals root x. The bottom of the slice was y equals 0. So that's why the total height of each slice was root x. Now, if you look at horizontal slices, you need to think about the right-hand endpoint of the slice minus the left-hand endpoint of the slice, right? X equals something, x equals something. You're right, y equals root x there, or x equals y squared, good. That's y equals root x or x equals y squared. Either one gives that equation.
Oh, okay. Y bar equals 1 over 2 times 1 5 y squared 2y. Yeah, minus x times 5y squared.
Or y times 5y squared dy. But it's not just y squared, actually. Well, y squared would be this distance from 0 to y squared. Y squared minus 0. That would be that distance, but you want this distance. So what's the right-hand side of this? X equals 1 to x equals y squared. 1 minus y squared is this width. Yeah.
What, why was it like, when did you divide it by, I'm just a little.
Where's this coming from?
Yeah.
This is the mass,
Oh, okay.
because if I want the mass, this is the mass of a slice.
Okay.
So if I want the total mass, I would just integrate
Okay, so 1 over mass.
equals 1 over this thing.
So.
Yeah, so you could do it again, and you should get 2/3 again for the denominator, because it should work either way.
So that was just the mass.
like you're just integrating them.
Yeah, yeah, I'm just finding the mass by an integral.
Okay.
It's just like finding the area.
Okay, I understand.
Sorry, yeah,
No.
good.
Yeah.
Is everybody getting there that the width of the rectangle is actually 1 minus y squared? It's really the right endpoint minus the left endpoint. Yeah,
Was there?
is it?
Wait, you,
Get a y bar less than, bigger than 1/2?
so my
Yeah, that's
equation
what-
for mass was
I heard that's what happened.
5y squared times dy.
Well, that's the problem, is it's not y squared. Y squared would be like, that would be the width of a rectangle like this would be y squared. Because that would be from 0 to y squared. So we actually want here to here. That's why it's 1 minus y squared, yeah. So then you should be able to do the same thing here. You can compute the bottom again if you want. You should get 2/3 again, because it's just the area of the, or 5 times 2/3, I guess. People getting answers? Did people get answers less than 1/2? That's exciting. Okay. So y bar, well, I guess I should say, so the rectangle, so the mass of the slice is 5 times 1 minus y squared dy. By the way, the slices are still 0 to 1, right? I mean, you have to check that. Where's the start and where's the end? Like if I'd had this go up or go farther over or something, it would be different. So you just have to be careful. Think about where the bottommost slices and the topmost slices. What's that?
Are you making your own problem for the test?
There you go.
No, are you?
Oh, yeah.
Okay, so there's no tricks.
Yeah, right. I'm making my own problems. So that's a good idea. I could do it from 1/2 to 1. In this, there'd be 2 integrals for the. So 5y. So this is what you guys got when you wrote it all out. I mean, you didn't have to recompute the bottom if you didn't want to, but the 5s cancel. That's one thing we should, I guess I should make. Actually, one thing with using the mass is that you have to remember that there was a 5 here. So I have to cancel the 5 out. But so I'm hoping this worked out to be 2/3 again. Yeah, this should work out to be 2/3 again, because it's really just, this is really just a different way to find the area of that region, right? You can find the area of that region with vertical slices or with horizontal slices. Ran out of board space. So curious. So curious where everyone got. Was it 2/5? No. Just guessing, because that was 3/5. Was that one was 3/5. So. What did people get? Someone tell me. 3/8? 3/8? 3/8? That's good. That seems plausible. You know what? We're sophisticates. We don't have to, I don't have to, you can do this. Wait, so that means the numerator was actually 9/16 or something? Huh?
1/4.
I can't do math. 1/4 divided by 2/3. Oh, you're right.
Can we just like write that on the
Times
exam?
2/3 is 1/4. Okay, the numerator is 1/4, right?
Can we just write that on the exam and call it good?
Well, this would be one of the things I wouldn't care as much about. I'd much rather care about the setup. But if your answer is wrong, then I'm gonna be like, I don't know where to give you partial credit from that little tweak. Yeah.
So since the 5 cancels out, just like outrated. Like, what's the usefulness of it?
Right, it's sort of funny, right? Because it's almost like it's actually just about like distances and areas and stuff, not really about mass at all. But that's because the density is constant. I mean, I could give you something like this where the density wasn't constant. The problem is that it would be really hard to find one of them. If the density was like a function of x, then you could find x bar not too badly, because you could still do the thing where the density would be constant on a vertical slice. So you'd have to throw in the density function, kind of like those problems I gave you with the triangle. You had to like find the width and the density function. But if it was a function of x, if the density was a function of x, it would make this really hard to figure out, the mass of this slice. In fact, you'd probably have to do an integral to find the mass of this slice. And then we're just doing multivariable calculus at that point. Might as well just teach you multivariable calculus. But yeah, but right. So it turns out, well, that's the question at the end of part of number 5. It says, question, would your answer have changed if the plate had a different but still constant density? And the answer is like kind of clearly no, right? Balance point should be just really depend on the shape, as long as it's constant density. So yeah. Okay, good. Should we need to take a break? Well, like you guys just had an activity. Didn't you go straight back in? All right, let's take a break for a couple minutes and then we'll come back and talk about work. Work is fun. Work is fun. Take a break for a couple minutes. Here, I'll pause the recording. All right. Hi, everyone. Only got 20 minutes left, so let's jump into this. So I have this just on the screen, the stuff about work. The idea is, right, so this is a physics concept, but it sort of is a nice application of integration ideas that like, so, you know, force is mass times acceleration. And so if you know, I always have to remind myself, I typed this out just so I can remind myself how the units work. Like force, if mass is kilograms, acceleration is meters per second squared. So force is kilogram meters per second squared, which is a Newton. Force times a distance is an energy. So that's kilogram meters squared per second squared. Is that what that is? Is a joule?
Yeah.
You guys probably know your physics stuff or your actual science stuff better than I do. Yeah, so right. So you would just multiply the force unit times distance. So you can say Newton meter, or you can say kilogram meter squared per second squared. That's a joule. And so like, right. So a lot of times, a lot of these examples, you do work against gravity, right? So like carrying something up is, well, I guess it's weird. Like you're doing positive work, but the gravitational field is doing negative work or something. That depends on who's actually doing the work. But the question is like most of the examples that you've seen in like high school physics and stuff of force of work is like force times distance is like a constant force times like a straight line distance. And in this class, we'll still do a straight line distance because the doing like along some curves and stuff really requires multivariable calculus again. So that's something we do in 1800. But here we will think about what happens when when the force function's either changing or you have an object. Like, so if like, there's two examples I wanted to do. One is like, if I want to like shoot some satellite into orbit, then the actual gravitational field changes as you go farther away from the center of the Earth. So the force is actually changing. And so you're going to need to like figure out the work done on each little subinterval of height that you're gaining, because it'll be a different force. You know, using Newton's law of gravitation will be a different force. The force will get weaker as you get farther away from the center of the earth, right? Or you can have something like this first example, which is where you have something like, these examples are kind of contrived, but like a cone-shaped tank full of water. And then you want to like pump the water out of the tank. And so it has to go above the rim of the tank. Actually, I think I said here in number 7, to a height 2 meters above the top of the tank. So you have to think about slicing the actual object, which is the cone of water here. And you have, at each height, you have a slice of water and you want to lift it at different height. So it's the same force, gravity. I'm not going to worry about the difference in gravity between 0 meters and 5 meters above ground. That's not very much difference in gravity. But it is going to be different. The top of the tank, the water at the top of the tank will travel less distance than the water at the bottom of the tank. So we're going to have to somehow, both of these concepts involve slicing. So let me just sort of think about this. So like I think I said in that 4th paragraph, yeah, the force is not constant, or the object is something like a liquid being pumped, so the different parts of the liquid travel different distances, right? So there's only one concept we've seen in this course so far, which is slicing, right? Like, I haven't even given you courses. There's like humanity. I think maybe I can't remember if I said this to you in the class. Humanity's only had like a couple of good ideas in our history, so we just exploit them as far as we can. Okay, we're pretty dumb. So, yeah. So okay. So work is force times distance. But what if either the force or the distance is not constant? Or the distance. That's kind of what we're kind of talking about here, right? By the way, I think I said this right, but the second half of the section, this is 8.6, I think, is like, or 8.5 or 8.6, I can't remember, maybe it's 8.5, is all about like force and pressure, and like the pressure on an object below sea level, if it's vertical or horizontal, like a wall or something. And my eyes glazed over and I was like, this is not math anymore, this is physics. So we're not gonna do that. We're just gonna do the first, because this has at least got enough math in it. So, I mean, it's interesting, but I just math. So, okay, so example. Let me just write this example. Stop the share. Okay. Good. Yes. Okay. Example. Let's do the cone example today, and then we'll do the gravity example class Wednesday. Okay, so we have a cone, a conical shaped tank. Height 3 meters, radius 1 meter. So that's 1. This height is 3 meters. And we want to, and it's full of water. So there's water filling up this tank. And I want to pump the water up to 2 meters above the top of the tank. So I don't know how to draw a pump or a hose or whatever, but it's supposed to be some sort of hose, the water going up. And you want to, and the question is, how much energy basically does that take to pump out this cone shaped? Because we do this daily basis, right? Kind of things we do with our life. We take water out of conical shaped tanks and compute the amount of energy necessary. So anyways, so okay. Now there's a couple things here. So we would want the mass of a slice, and then we want the force on the slice, but that's mass times gravity, right? Mass times acceleration. So the idea is each horizontal slice of water has a certain mass mass. Okay, so then, and then mass times gravity is the force. And each slice travels a certain distance. But it's different distances, right? Like the bottom has to travel 5 meters and the top has to travel 2 meters. So each slice travels different distance. So what's the first thing I do in all of these problems? Green chalk. I draw an axis. So here's a y-axis. And let's just call y equals 0 down here. Y equals 3. I guess y equals 5 is there, right? And we want the slice at height y. So the slice, so consider the slice at height y. Let's see. What is the, well, okay, so what is it? It's got a thickness d, it's got a thickness dy, right? So the volume is the area times the thickness. So this is just like the integrals we did for calculating volume before, right? So this is dy. This is pi r squared for some r. And remember how we found the r? I think we have to use the similar triangles thing, right? So we have this triangle inside and then the big triangle here. So the big triangle is 1 and 3. And the small triangle, well, it's upside down, it's nice. So it's y and r, right? Remember upside down works out nicely. It's not 3 minus y, it's y. And so r over y is 1 over 3. So r is 1/3 y. Makes sense. This radius is 1/3 the height. So at height y, the radius will also be 1/3 the current height. Okay, good. Remember doing a lot of this? Done this on homework and stuff already. This was the side view, flattened side view. Okay, so then the volume of the slice is pi times 1/3 y squared, oops, y quantity squared dy, which is pi over 9 y squared dy. Now, what about the mass of the slice? Well, we need the density of water, actually. It's 1 gram per cubic centimeter. We have kilograms and meters, so I think it's 1,000 kilograms per cubic meter. If you do the conversions, you have to multiply, you have to switch centimeters to meters, but cube grams to kilogram. I think it works out to 1,000. So the density of water is 1 gram per cubic centimeter, or if you convert, it's 1,000 kilograms per cubic meter. You can check the conversions yourself. So the mass of the slice, we would just multiply by 1,000. I mean, this volume actually should be in meters cubed, right? This is meters, squaring it, dy is in meters. So we have meters cubed. And so the mass of the slice is 1,000 over 9 times pi times y squared dy kilograms. You just gotta go through and figure out each piece as you go, right? That's the mass of the slice at height y. Good. Now, the next question is, how far does this slice has to travel? Does this slice have to travel to lift this slice of water up to the top? How far does it travel? The slice at height 1, how far does that have to travel? We're going up to 5 meters. So what is it? What's that? Yeah, like just as an example, at height 1, how far does the slice have to travel? Travel 4 meters. At height 2, how far does it travel? Yeah, at height y, how far does that travel? 5 minus y, right? Works for certain examples. So then, right, so each slice travels a different distance. So the slice at height y travels 5 minus y meters to get to height 5. Okay, so now force times distance. Oh, so we had the mass. I don't have the permission to do this update and it keeps asking me. I can't. Sorry. Go away. Go away. No? Okay. Sorry. Doesn't matter, I guess. Does that make sense? It has trouble 5 days. Okay, so I guess one thing I forgot to do, sorry, was the force on the slice. The force on the slice is actually mass times acceleration, gravity, right? So I probably should have said that first. The force on the slice is mass times gravity. Which is 9.8 meters per second squared, right? Okay, so 1000 pi over 9 y squared dy times 9.8. I mean, I guess this is kilograms. This is meters per second squared. So 9.8 times 1,000 is 9,800. Sure, I could make this some nicer number, maybe, but. Okay, so that's the force on the slice. So basically, these are the two numbers we have. We have the distance the slice has to travel and the force on the slice. All right, I guess this is newtons. That's meters. So really, it's just the product of those two is the work done on that slice. So the work done on the slice is force times distance. That's 9,800 pi over 9, whatever number that is. Y squared dy, newtons times meters times 5 minus y. And so we could write that as like 9,800 pi over 9 times y squared times 5 minus y times dy. Okay, so that's the work done on the slice. Makes sense. Put it all together. And so then to find the total work done, we'd want to integrate this over all the slices, right? We're basically adding up the slices. Where are the slices range from what y equals what to y equals what? It's just 0 to 3, right? Because the top of the tank is at 3. So just don't make a mistake and actually do 0 to 5 or something like that. But bottom is y equals 0. Top is y equals 3. So the total work is the integral from 0 to 3 of this 9,800 pi over 9 y squared times 5 minus y dy. And the truth of the matter is I don't really care what that equals. It's going to be some number that doesn't mean that much to me. You can factor out the 9,800 pi over 9. You can multiply the y squared through here. 5y squared minus y cubed, right? You can integrate. So let's just say that equals some number. But as always with these, it's the setup. It's the setup, right? You got to draw the picture carefully. You got to think about the slices carefully. You got to think about where the slices are. You got to think about the shape of the slices. You got to be able to find all the requisite distances and stuff that's involved in the slices. And then, you know, you got to build up to force times distance, like piece by piece by piece, right? Volume times density gave us the mass of the slice, mass times acceleration gave us the force on the slice, force times distance gave us the work of the slice. Okay, cool. So Wednesday we'll start with number 8, which is a little bit different because you're actually, like I said, it's one object, it's like a point mass kind of being raised to a certain height, but the force is changing because it's going through a long enough distance that the gravity is actually changing as you're getting farther from the earth. So you might think about number 8 before class Wednesday if you have a chance. Okay. All right, everyone. I'll post the homework post haste, forthwith, whatever. And I have office hours today. But I'm not available. I actually leave like after class Wednesday. So so I have tomorrow afternoon, I have the office hours this afternoon, tomorrow afternoon, and Wednesday morning. And then Sarah will have study group Thursday night. Plus there's the tutors across the hall in the evenings and stuff. So, all right. Take care, everyone. Have a good couple days.